Hello, everybody, and welcome back to A Deck of All Jacks. I am your host, Peter. I have today with me my friend Runi. You are listening or watching the show where we invite ordinary people on to talk about the things that they are the most passionate about. And I have my wonderful, wonderful friend Runi. Say hi, Runi.
Hello, everyone.
So, Runi, how are you doing today?
I'm doing well, Peter. How are you?
I'm doing well. Have you ever been to Buc-ee's, Runi?
No.
So they just opened Buc-ee's in Arizona for the first time on Monday. And I got to go to Buc-ee's, which for those who don't know, Buc-ee's is I would call it almost a hybrid between a gas station and a Walmart. It's got like 30 pumps. It's almost a little mini mart in there. They have all these different things. You can get Texas brisket. You can get fudge. I got a selection of different fudges and brought them back home. And my brother and I have been going through that, so we've been having a good time. And it's summer break as of the recording of this, and so I'm happy to, as a teacher, have some time off, which is really nice. I have a list of different things I want to kind of talk about based on your own suggestions about what you know and what you're passionate about, Runi. But before we get into those, tell us, who you are, what do you do for work, stuff like that.
Hi, I'm Runi. I am a software engineer for work. I studied math in college. Um, yeah, I probably will get into it more, but I enjoy all things programming, writing, uh, reading. I don't know.
Very cool. But then how do we know each other, Runi?
Yeah, so we met in college. We were on the same floor freshman year.
Mm-hmm.
So it was the Humanities LLC, Humanities Living Learning Community. And I think both of us, a lot of our friends throughout college were made on that floor, which is pretty cool.
Yes, I probably talked to people from that floor, maybe 10 or so of them, at least enough to keep up with what they're doing. And I would say maybe 2 or 3 on an actual regular basis. But yeah, it was a floor dedicated to people, really freshmen, who were interested in the humanities. Rooney was down the hall from where I was. Also on that floor was Diana, who became Rooney's wonderful girlfriend freshman year. And you guys have been dating now for how long?
6 years almost.
Wow, you guys are a very cute couple. Congratulations on that.
Thank you.
The audience might be able to even hear Diana a little bit in the background, doing some stuff around the apartment. I will be very happy to have Diana on here as well sometime soon to talk about what she's passionate about. But to give some background for you, Rooney, to my recollection, I remembered you had lived in the northern Chicago suburbs. I guessed Evanston. I was incorrect. It was actually Vernon Hills. So tell me about growing up in the Chicago suburbs, especially because actually the first guest on my show, Ben, on last episode, he was from Southern Illinois, so he was from the St. Louis area. And you're basically on the polar opposite end of the state, being not only from Chicago, but the northern part. So tell me what it was like growing up in Vernon Hills.
Um, well, so for context, I moved to Vernon Hills in around the 4th grade, but I still consider it where I grew up. Before that, I spent most of my life in Atlanta, but a lot of my memories are from Vernon Hills, and I guess it's an interesting question to ask, what it's like, because I don't really have a frame of reference, I guess, for what else it could be like. I don't know. I live in Boston right now, so the weather was pretty similar. 4 seasons. I lived in the suburbs. Um, yeah. Fun fact, and I can't stop telling people this, but 4 years above me in my high school was Jalen Brunson, who just won the
Whoa!
championship for the Knicks.
Yeah,
I can't stop telling people that right now.
go Knicks! Oh, that's wonderful. Is your high school known for having a good basketball program, or was he the exception?
At the time, we were. I think he won a state championship for us.
Wow.
I think we're pretty good pretty good at sports. It was a pretty big part of our experience. being a large school too, I think there was just a lot of different sorts of people. Like for context, each class was like around 1,000 people, so we both went to Dartmouth. It's pretty similar size.
Okay.
But for a high school, I guess that's somewhat large.
Was it at least a nice high school with pretty big grounds, or were you guys kind of crammed together in there?
No, it was nice. We had a lot of space, a lot of athletic facilities. Yeah.
Okay. What kind of stuff were you involved in high school? Were you doing basketball just like Brunson, or?
Oh man, I tried.
Yeah.
But no.
I didn't know that.
But what was I doing? Honestly, I didn't really do a lot of clubs. The main club I did was science fair, if you could call it that. It's kind of more of an individual activity, but that was something that I did for all 4 years. That's where I kind of found and developed my passion for math. I had the opportunity to go to the Intel Science Fair in, I think it was in Pittsburgh at the time.
Okay.
Which was definitely like a highlight experience of high school for me.
Was it at Carnegie Mellon or was it somewhere else?
No, it was in a hotel, a convention center.
Well, my last guest also was involved with science club or like something adjacent to that in high school, and that's how he found his passion for geology. And so I'm glad that you also were able to find a love for STEM in that. When it comes to math, I asked you, kind of leading into this, I was like, Runi, could you tell us, because you're very knowledgeable about like higher level theoretical stuff with math, and I asked you for stuff that like maybe would potentially be something that like the average person could wrap their head around, and you responded with decomposition problems in math. So what is up with decomposition problems?
Yeah, so I'm, especially now that I don't do math full time, I'm more, do it for enjoyment. One of the things I really enjoy about math is broader philosophies.
Okay.
And I think a really central one, and there's a lot of ways of phrasing this, but the broad idea is you take a complex object and you ask, what is the simplest type of that object?
Okay.
And then how can we build up the more complex thing from these simple pieces? So it's basically like, like molecules or whatever, and you try to figure out what are the atoms of this structure, and then how can we, piece them together to, to form the more complex thing. And there's like a lot of variations of that, because it's like, what does it mean for something to not be decomposable? Like atoms, we sort of say that it's indecomposable, but we know that there's things inside of atoms, but
like protons, electrons, right?
Exactly. Yeah. So that's one question, and then obviously, like, chemistry would be very easy if everything in the world was made up of entirely, hydrogen atoms.
Yeah.
But that's not the case. There's different atoms, and there's rules for how they can come together, and yeah, that's the broad philosophy. And throughout math, you'll see this idea popping up. And I think that's a really cool thing about higher level math, is you have these broad ideas and you just see the ways that mathematicians explore it and apply it to their own domains. Like you have people who are interested in statistics, and you have people interested in geometry and, whatever. But they're all sort of asking the same flavor of questions, just in different settings.
So when it comes to these, you said complex structures, simpler parts. Is there any example of a complex structure that people would already be familiar with or can easily conceptualize?
Yeah, so when I was thinking of examples for this, like the one that I was most recently thinking about came to mind, which is linear operators, aka matrices. But I think like an even more simple example, if people are not familiar with that, is like polynomials. We all learned, I think, in high school that there's roots of a polynomial. You can factor a polynomial.
So a polynomial would be like 3x squared plus 2x plus 1, something like that, right?
Yeah, exactly.
Where there's like, you have like a regular number like a 1, you have the x as the variable, and then you start having like your x squared, and because there's all these different these different types, they each have their different names. You have an integer like a 1, you have the x squared, because there's multiple of these. It's a polynomial. There's a few different ones within the same kind of sequence, right? So yeah, keep on going.
Yeah, so like take x squared minus 4, for example. So you can factor that pretty easily. You can actually completely factor it, you could say, because it's, parentheses x plus 2 times parentheses x minus 2.
And so what is factoring again? I kind of forgot.
So factoring is breaking up a polynomial into simpler polynomials.
Okay.
So, like if we take this x squared minus 4 example, we call that a degree 2 polynomial because it's like there's this x squared term, right?
Yeah.
So a degree 1 polynomial would just have x. That would be like x minus 2. That's a degree 1 polynomial. Or x, just by itself, is also a degree 1 polynomial.
Okay.
And to go even further, like just a number, like 2, you could regard that as a degree 0 polynomial. There's no variable.
Is there such a thing as a degree -1 polynomial?
Not in this setting.
Not in this setting. Okay, in other settings you can have that.
Yeah, I feel like there's ways you can make sense of that, but for this discussion, let's say no.
Okay, gotcha.
But so then what are the atoms here, right? So the first observation, I think, is that if you multiply any two numbers, just plain numbers, you're never going to get x, right?
Sure.
You're never going to get this random variable out of nowhere.
Yeah, you can't get 2 times 5 equals x, 2 times 5 equals 10.
Right. So you can't ever, decompose a polynomial like x squared minus 4 into just like 2 times 5. That doesn't even make sense. There's like no sequence of numbers for which you could do that.
Yeah.
So then you're like, okay, what's the next best thing? Is you need at least one x.
Okay.
And then you could say like, oh, x times x. I can build up x squared by just taking x and multiplying it by x. So in a sense, I broke up x squared into x and x.
So that would be essentially 2 atoms, just each atom is of the same type.
Yeah.
Okay.
So let's take it a little bit further. Now we have x squared minus 4.
Okay.
So you can do this calculation on paper, but I can tell you that it breaks up as x minus 2 times x plus 2.
Sure.
Now x minus 2, for example, that doesn't break up any further.
But isn't that still a molecule where there's the atom of the x and the atom of the minus 2?
So molecules here we're meaning like things you multiply.
Okay, gotcha. So x minus 2 is itself an atom.
Is a thing, yeah.
Okay, gotcha.
So that becomes the most fundamental atom. So in other words, to say it specifically, like degree 1 polynomials are like our atoms.
Okay.
And so this is actually a rich idea. Like if we just put polynomials aside, if we ever talk about higher dimensional structures, which mathematicians do a lot, and I realize that's really abstract if you're not.
When you
talking
say
about it
higher
all the time.
dimensional, I mean, I know like the Empire State Building is a 3-dimensional structure, but are there more dimensions that you can have for a structure?
There are. And it's not as mind-blowing as people might think. Like,
okay.
if you like just write down a list and you say there's 4 things I could put in the list,
Yeah.
and I could put any number in any slot of the list,
Okay.
then you're already talking about a 4-dimensional structure. It's just not a spatial structure, right? Like you're not talking about a geometric structure necessarily, but like higher dimensional stuff is all around us. And I think that's also ties into my programming or computer science interest.
Yeah.
Is people think like, oh, studying higher dimensional stuff, like why would that ever be useful? But it's useful all the time. A lot of the stuff that we do in the real world just has a natural setting in, higher dimensional structures.
So if I have a grocery shopping list and I have milk, eggs, butter, and cereal on it, that's a list of 4 things. That would technically be a structure with 4 things, or like a 4-dimensional structure, just not a spatial one.
Yeah, exactly.
And so then when you're coding, you would have certain lists of things like run the program A, program B, program C, and program D, and then that is itself a 4-dimensional structure. Add program E, it's a 5-dimensional, etc.
Yeah, exactly.
Okay. And when you have coordinates, you have your x, y, and your z coordinate, right? So it's like the latitude, longitude, height, or whatever. And then if you add in like maybe t, it would be like the time, right?
Yeah.
So that already, technically, the Empire State Building right now, if you put together its latitude, longitude, how tall it is, which is rather tall, and the time of like what the time currently is, that would be assigning it 4 different things on the list, which would be a 4-dimensional structure in a sense.
Yeah, and theoretical mathematicians and physicists work in that setting all the time. They literally talk about a space, like a geometric object called space-time.
Yeah.
And it's kind of like that.
Because when it comes to physics, time is an additional dimension of space. They're seen as the same, not quite the substance, but like the same thing, right?
Yeah.
Okay.
And this is really mind-blowing. Like your example, like us being right here, we have a position and we're at a point in time. And as time goes on, we're doing different things. My hand's moving like this. So not only is my position changing, but across time, my position is changing. So what's really happening is a path through space-time. And I literally mean like a path, like if you just take a paper and you're drawing a point, that's a path, right?
Because
yeah, go ahead.
Well, because humans can time travel in the sense of we're constantly moving through time at the rate of 1 second per second. This is just like the passage of time, right? When it comes to movement in the other 3 dimensions, we can speed that up or slow it down. So like I can decide to like move faster horizontally or move slower or not move at all. Whereas time, we're kind of bound by this 1 second per second pacing. Is it conceivable of either humans unlocking or like other creatures like aliens, if you want to, who like are able to move through time at different paces, or are all things in the created universe bound by this 1 second per second thing? Do you know?
I can't say for sure. I will probably embarrass myself trying to answer this because I'm not a physicist, but
Gotcha.
I do know, for example, time.
Well, because they've sent astronauts into space, and because of like, isn't it like because of how fast they're going or something? Like they're technically like a nanosecond like younger than the people on Earth because of that.
Yeah, there is like a relationship between the speed you're going at and time relative to people not going at that speed. But so maybe you should get a physicist on.
Yeah, I think that's definitely fair. I think I've seen enough sci-fi. I think Interstellar touches on this.
Yeah, I watched Interstellar as well.
Yeah, Interstellar, it's like if you get fast enough of speed, then you can like kind of slow down your own aging. But that would be slowing the pace of time. I don't know if we'd be able to speed it up.
Well, so the interesting thing is you're not slowing your aging, right? Like wherever you are, I guess maybe this answers your question. Wherever you are, you're experiencing time the same.
Okay.
It's just that people who are, so let's just take Interstellar, right? Like
Yeah.
they're going really fast around this planet.
Yeah.
They're near a black hole, so there's this time dilation.
Yeah.
And they send people down to the planet. They spend, from their perspective, 30 minutes, and they come back up to the spacecraft and spend 30 years
Yeah.
on the spacecraft. So, I mean, for the people who went down, they experienced time normally. So did the people in the spacecraft. But when they reunited, there was that disconnect.
Would it be essentially the same as someone who like walks 30 miles versus goes 30 feet, and then they just end up meeting back at the same location because the one going 30 miles went 15 miles one way and 15 miles back? Or is that not
That's an interesting intuition.
I don't know if that's right or all. I should definitely get an actual physicist on here, or a friend who like at least studied physics in college. But you were so back with these decomposition problems. You mentioned matrices. Are there any other things that have these multidimensional things that you would interact with, either as a theoretical mathematician, as a coder? Like, what are some other examples of these multidimensional structures?
So, yeah, like matrices are a big one. That's kind of the area I was in, was
I mean, I think
functional
of
analysis.
a matrix, beyond Keanu Reeves, I imagine like a bunch of numbers like on a grid. That's what matrices is, right? Like on a two-dimensional grid.
Yeah.
Okay.
Yeah.
How is that
So,
four-dimensional then, if they each... Yeah.
Well, so a four-dimensional... So, matrices are, like you said, grids, right?
Yeah.
So when we say a 2x2 matrix, we mean a grid that's 2 rows and 2 columns.
Okay.
So as an object, there's four slots, right?
Yeah.
So like the matrix itself is four-dimensional, just by nature of having 4 slots.
Okay, gotcha.
But actually, like that's not usually how we think about it.
Yeah.
What matrices actually are transformations, linear transformations, if that means anything to you.
What's a transformation?
Yeah, it's just how can we... So if we have like a geometric object,
Mm-hmm.
how can we like change it into another geometric object? That's just a transformation.
Like changing a triangle into a square by adding a side.
Yeah, for instance.
Okay. Gotcha.
Usually when we say linear, we mean though like, okay, you have this two-dimensional object. You can either rotate it, you can stretch it out, shrink it down, or like if it's affine, we mean you can just like shift it.
Well,
So
anytime I move my mouse, my cursor moves left or right or up or down. So that's essentially just a transformation, right?
Yeah, exactly.
Okay. Gotcha. I'm following so far.
So what matrices are linear transformations of spaces. So let me just give an example of the 2x2 matrix. The reason we call it a 2x2 matrix, and we always refer to it like that, is because fundamentally that's a transformation of two-dimensional space to two-dimensional space.
Okay.
So imagine you had a piece of graphing paper. We can call that a two-dimensional vector space.
Sure.
It's jargon, but, just for intuition.
Because you can go up and down and left and right on the paper, but you can't go like...
Yeah.
You can't change your height. You're just always on that
Exactly.
same height. Okay.
Yeah. So a matrix says, like, if you draw something on that graphing paper, apply the matrix, I'm going to tell you how to draw it again on the graphing paper. So let's just take like scaling, for example.
Okay.
I can write down a matrix that will stretch everything by 2. So if I drew a line, it would be, after my transformation, twice as long.
Okay.
So, or like if I had, a triangle and the pointy end, I guess they're all pointy ends, but
Sure.
like it's,
The top
straight.
pointy end.
Exactly, yeah. I could tell you a matrix that if you applied it, whatever that means, it would turn upside down.
Is it because the matrix has numbers on it and those numbers are used to input new values, like a new x and y coordinate for where the different points go?
Yeah,
Okay.
exactly.
Gotcha.
So that's really how you should think about matrices, is they're transformations of space.
Are they not just collective coordinates and instructions used to make those transformations? Or do I have that incorrectly?
Yeah, but that is the transformation also.
Sure. Because all you need in order to do the transformation is the matrix, because it's the one transforming it. Okay.
Yeah.
Gotcha.
So, in 3 dimensions and in 3 dimensions we have computer graphics, right? If you ever thought about when you're playing a video game,
Yeah.
how are they showing it? What does perspective mean? Like, how is my camera moving around the scene?
Sure.
What your computer literally, like very literally, is doing is constructing matrices for your camera, 3x3 matrices, maybe 4x4, but that's a topic for a different time. But let's just say like 3-dimensional matrices, and they're just multiplying everything in the scene by that matrix, so that now it's all from your perspective. So it's transforming the entire scene to be viewed from your perspective.
So if I'm playing Super Mario 64, which is known for being like the first big, like popular 3D game, I have Mario on the screen. He's in front of me, running around the castle, and kind of separate from Mario running around, there's me. I'm like the camera operator, and based on the inputs of my controller, that's creating a new matrix. Every single every single second, or I don't know what the word would be.
Frame.
Yes, every frame.
Yeah.
Every frame, it's creating a new matrix based on my input, and then with each new matrix, that matrix then transforms the scene by commanding the camera to move, or what is the matrix commanding exactly?
So, given if I tell you a scene, and I tell you where the camera is in that scene,
yeah,
I'll generate a matrix that shifts everything so that the center of the world is that camera. And
so it's physically changing the world of the video game?
Yeah, it's moving everything.
Oh, I thought it was just like a preset box and it was changing my location. But no, it's changing the whole world around me to fit my perspective, because otherwise it would look really wonky. It wouldn't look real. Like the horizon line would be all messed up.
Yeah. Like when we view the world in our everyday lives, we're kind of viewing it as if we're the center of the world, right? Like everything is around us. So it's the same principle.
Because that's just what perspective is just being the center.
Yeah, that's perspective. Yeah.
And so constantly the game is transforming the world every single frame. And this is true for any 3D game nowadays, even the barely high-tech, like movie budget looking, like war games and stuff.
And you can imagine that's very expensive for your computer to do. That's hard. And slight tangent, but that's where graphics cards come into the picture. If you ever wondered what it's really doing, a graphics card, they are thousands of really simple, really small computers. Like your CPU is just one computer, right? Maybe it has a couple cores, but it's just one computer.
Like my laptop is one computer, because that's what it is.
Yeah.
Okay.
And then we have this alternative thing called a graphics card, which is a bunch of tiny computers that they can't do much, but what they can do really well is multiply matrices together.
Okay. So the graphics
So,
cards aren't actually showing me the image, but they're creating the matrices that the video game console uses to then
oh yeah,
calculate what to show me.
they are just crunching numbers. They are not
Wow.
really displaying anything. Which is why, nowadays graphics
Mm.
cards I feel are always mentioned in the context of AI.
Yeah.
Why can you do that? Because it's not about graphics, it's about crunching numbers. And as it turns out, AI training involves a lot of matrices and linear algebra.
And why does AI need all these matrices again? Because it's not creating a perspective for me in a video game. What's it doing instead that it needs all these calculations for?
Yeah, so, like again, matrices as transformations of a world or a scene is one interpretation of it. It's the interpretation when you apply it to the three-dimensional spatial world. But
Okay.
we just talked about like lists of numbers are higher dimensional objects. And as it turns out, and it gets a little bit technical, but the way AI trains itself is, involves a lot of linear algebra. A lot of like, you have these huge lists of measurements and parameters, and it's finding like just the right way to transform things so that it's a little bit more optimized.
Because when I talk, or type into ChatGPT, what it does, how generative, to my best understanding, and correct me if I'm wrong, what generative AI does is it predicts the next word, or even just predicts the next letter. Of like, if I say, where is the closest Domino's to me, and I give it my location, it's going to predict, not necessarily calculate, but predict through language that, like, it would be this number, this street address. And so how does that work with predicting the next input and then matrices again?
Um, it's it's admittedly technical.
Okay.
But at a high level, you're talking about like, just imagine there's like a cost associated with an AI's response. Like you can score it, let's say.
Okay.
It's like, okay, you did a good job, you did a bad job.
Yeah.
And for every input, you can like say, did I do a good job? Did I do a bad job? Like how good of a job did I do? How bad of a job did I do?
Okay.
And the goal of training an AI is to optimize its responses, optimize its behavior so that it's like the most good, right?
Okay.
And this sort of optimization problem is the bread and butter of calculus.
Okay.
And what is calculus? Calculus is the idea that you have these functions, and it's asking like, in what sense can I zoom in really close and it starts looking like a linear transformation.
Yeah.
So I'm probably throwing out way too much jargon, but at its core, what a derivative is a matrix. So calculus and linear algebra are like inherently linked.
Mm-hmm.
I don't think a lot of people ever learn that, whether they studied STEM or not. They're inherently linked. Optimization problems where you ask what's the most optimal way to do something.
Yeah.
That's calculus. And so extrapolating, that's sort of how gives a sense of why calculus and linear algebra are important for AI.
So, I mean, AI is, as many are saying, one of the, if not the biggest transformation for the workforce, potentially human society. And you're saying it is completely dependent on both algebra and calculus in order to like function, grow, improve, and all these things.
Yeah. What an AI model is just a really optimized mathematical equation.
Okay. Yeah, because everyone always says in Algebra 1, Algebra 2, even pre-calc, like, oh, when will I use this in real life? And if it's literally the driving force behind the driving force that is radically changing our workplace, then that is a very radical thing, for sure.
Yeah.
We are going to take a quick break. I'm going to edit it as if it never even happened. But when we get back, I'm going to ask you, Runi, about small talk, programming languages, and computing philosophy.
Cool.
All right, and we're back with no time lost at all for you at home. We've been talking a lot about computers, languages. For one of the topics that you suggested, you said Lisp, small talk programming languages, and computing philosophy. And I don't know what most of those words mean together. I know what each of them mean separately, but tell us more about these things.
Yeah. So when I say a Lisp, I mean a family of programming languages.
Okay.
So, and same with Smalltalk. So if anyone's unfamiliar with what that is, we generally write computer programs in a language somewhat similar to English, at least something that humans can read.
Sure.
And there is another program called a compiler that takes this human readable description of the program and through various steps converts it to the machine code, the zeros and ones that the computer actually runs on your CPU. So programming languages themselves are like user facing, they're human facing, and there's lots of different opinions on what's the most aesthetic way to have a programming language. What are like our design goals? What are the things we want to make easy? What are the things we want to make difficult?
Why
like
would
for example,
why would things be difficult?
Yeah, like programmers, if you give them a way to do something dumb, they're probably going to do it. So if you have a footgun in your language that makes it super easy to say, take all the memory from your computer and just never release it.
You want to make sure that potentially big mistakes are hard to do so that they're not accidentally
Yeah.
made. Okay.
Exactly. So it's a really interesting programming language design, which I'm really interested in. It's a really interesting like intersection of not just, like the technical aspect of computers, but also of design and of like how humans interact with programs.
Because I took Introduction to Computer Science in college, mainly to get my math credit out of the way. And when I would like create Pong, which that was one of the assignments, I would have to be like / I don't know what I think it was C+. I don't remember I think maybe, no, it was Python. It would be like, I don't remember what it was exactly, but it'd be like / transform paddle 1 up 2 or whatever, if I, press up on the keyboard. And that's like it's not like the same as a sentence, but it is like A, B, C, D, like transform, Pong paddle, up to, if, and you can like intuitively see that. And I'm assuming with computing philosophy, with programming languages, you want to make sure that like everything that you're supposed to do is understandable like that, or there's some philosophies where that's not the main priority.
Yeah, that definitely clarity is a huge one.
Yeah.
But also clarity means different things depending on what you're doing.
Okay.
If you are writing a, I don't know, something like a Pong, like you are for CS1.
Yeah.
You might not care about the same things that, say, someone who's writing your operating system cares about.
Okay.
Or someone who's writing, the code that runs on your microwave is caring about. So
what would the microwave coder care about that I wouldn't really care as much about?
So the microwave coder is working on a really, really slow and limited machine.
Yeah.
So the unit of memory, which is like data that you can have in a computer at once, let's call it a byte.
Yeah.
Right? Your laptop, even a pretty entry level laptop, is going to have gigabytes of memory. Gigabyte is like 1 billion bytes. That's a lot of memory.
Okay.
Your microwave, I mean, I honestly don't know, but it might have like kilobytes. It might have thousands of bytes,
So my microwave is dumb because all it needs to be able to do is like heat something for a certain amount of seconds, like display the time. Yeah. Okay.
But because it's so constrained, right? You don't have unlimited memory. You don't have gigabytes of memory.
Yeah.
You have to be really careful about how you are using what you are given.
Oh, because they still want the microwave to do as many cool things as it can with its dumb brain, because then it'll sell better.
Yeah.
But they're not going to make it too fancy, so there's like a medium, because you don't want it. You want it to be like smart enough to do like enough cool things that people are happy with it, but you don't want to give it too much brains, because then you're just wasting money on, like, I don't know what if it'd be like CPU or graphics, but you're wasting money on stuff that people don't actually need.
Yeah, exactly. And that informs design, because I bet when you were writing your Python, you said maybe, create ball, or create a list, or create this thing. And you didn't really think about how the computer did that. Where did the computer put that? It had to put it somewhere in memory. It took some bytes.
Yeah.
All of that was not even a question for you when you're using Python. And that's by design, because whoever wrote Python, he said, I don't want you to worry about that, because I want you to be able to write Pong in a CS1 class. I don't want you to need a degree in CS to write Pong.
Mm-hmm. Yeah, it's supposed to be very user-friendly, which then...
Yeah.
So then it wastes some potential that could be used for other stuff in order to make it easier for me to make Pong. Okay.
Yeah, so at the other extreme, you have a language like C, which is probably what the program that runs your microwave was written in.
Yeah.
And in a program like C, there's no such thing as telling the computer, go figure out where to put it. I don't even want to think about it. In C, you have to always explicitly ask, give me like 10 bytes of memory.
Yeah.
Now that I have it, I'm going to use it for whatever I want to do. And I also need to tell the computer, here's your 10 bytes of memory back. Because if you're writing on a microwave and you don't have many bytes available to you, you don't want to hold on to it forever if you're not using it. You're going to run out of memory.
So by being so precise and exact in the instructions, you're not wasting time on like all this fluff. You're like doing exactly what you need to do and not doing anything else. And then that gives you more availability to use that memory and other stuff that the microwave can do, like, heat potatoes differently from meat and stuff like that.
Yeah, yeah.
And then what are Smalltalk languages?
So Smalltalk is a family of languages that epitomized what we call today as object-oriented programming.
Okay.
So, these are languages like Java, C++, and it's gotten a bad rep for reasons maybe we'll go into, maybe we won't, but at its purest, it's this idea that everything in your program is an object. It's this abstract thing. We're just going to call it an object.
Yeah.
And objects communicate to each other. So, like, if you have different components in your system, they're objects, and you want one to tell the other something to do, you send messages between objects.
Okay.
And when an object can, receive a message, of course, and when it does, it says, okay, what was the message? Okay, they want me to do this thing. I'm going to go do that thing now.
Okay.
So it's this really one of the ideas that really I love which is this like, I want to call it like an anthropomorphization of computing.
Sure.
It's this like idea that we can write code in such a way that everyone is like a little, like little citizens working together as part of like this big, civilization or ecosystem to produce an effect. So like take your Pong example. Like you might say, okay, there is a thing called a ball and there's an object called a paddle.
Yeah.
And there's an object called your keyboard or whatever controller you're using to input.
So that
and whenever you
so that would be conceived of as a separate object by the system, like my keyboard, and then my mouse is its own object. Okay.
And when you move your mouse, that's the mouse object sending a message to, your game or whatever.
Yeah.
That I just moved. Do something about it. And whoever's listening is going to say, oh, I care when the mouse moves. I want to move the paddle object. So then it sends a message to the paddle object and says like, hey, move up.
Yeah.
And so that's sort of the idea.
So you have almost a little civilization within a video game. You have the mouse who's like kind of bossing around the paddle because the paddle's trained to communicate with the mouse and do whatever the mouse tells it to do. But then like the ball is its own social unit who doesn't need to listen to the mouse. The ball just has a completely separate function. But because this whole thing operates in the way that a little community does, you like that a lot better as a type of system.
Yeah, and I think you're alluding to the next logical conclusion, which, as far as I can tell, wasn't really part of the original Smalltalk idea, but all of a sudden you have these objects and you're like, okay, I need a way to organize them. Like, what do we do in society, People are part of institutions.
Mm-hmm.
People are not always, talking to, other people. It's institutions sometimes interacting with institutions. Because that's the more optimal way to do things.
Sure.
And so it's like, okay, maybe we group objects into like game controller institution.
Yeah.
The game, like the controller system. And then we have like a graphics system or a physics system. And there's this sort of like, I really feel it's like a civilization. Like these abstractions sort of come out of necessity of like the scale that you're talking about. If you have 1 million objects, these things come out, sort of naturally.
And what are the types of programs that would use these type of languages? Like I know Minecraft is built on Java, which you mentioned. Are these used a lot with games? What are these generally used for?
So this sort of like ways of programming like this, like object-oriented programming, is what we call a paradigm.
Okay.
And for the most part, you could write any program in any paradigm.
Okay.
Right? It's just a way of structuring your program. It's just a way of thinking about the problem, which is, I think is pretty cool. Like you could say, what I was just describing with these objects, like maybe that resonates with you, but maybe it doesn't. Maybe you're like, that's, that just seems kind of superfluous. And then you don't write your program that way. But people like the creator of Minecraft, or funnily enough, a lot of corporations in like the 2000s, 2010s, thought this is like a really great way for people to write programs, especially when we have thousands of employees. If they're all like writing their own objects, maybe that's the right way for a big company to write a program.
Okay.
So they do it that way. But to your point, if you're writing a program for a microwave, you're probably not going to do that because you're introducing a lot of like fluff, as you would say, when you're structuring everything like an object. You're sending messages Like, why do you send a message when you can just tell the computer what to do?
So the programming language almost reflects the institution that uses it, because if a small talk language is essentially like a little society or a little corporation with like bosses and underlings and stuff, then it would make more sense for it to be used by an actual corporation, right?
Yeah, at least that's my theory. But yeah.
Okay. So not art imitating reality, but programming language imitating reality.
Yeah.
Yeah. Okay. Very cool. Do you have anything else to say about programming languages?
Yeah, and so I talked about Smalltalk, and it ties into Lisp. So Lisp is another family of programming languages, and I think its big idea, along with Smalltalk, is that it's what we call image-based computing.
Okay.
So it's this idea that your program is a living thing, in a sense. You run your program, and okay, well, let me back it up for a second, because I think it's more fascinating if you think about how we write software today.
Yeah.
So the model that won is how we write software today. You write your code in a text file.
Mm-hmm.
You put it through a compiler, and then you run it.
Sure.
So, and I think if you've taken CS, I think that's just like you kind of wonder, why would you do it any other way? Like, what does it even mean to do it any other way?
Yeah.
But these image-based programming languages like Lisp and Smalltalk, they're like, no, your program is running. Change it while it's running.
Okay.
Like, what if you were, playing a game, you're writing your Pong game, and all of a sudden you're like, hey, I don't know, like something is broken with my input. When I press the up arrow, it actually goes down.
Yeah.
Like, that's a bug. What would you do normally? Normally you'd quit the program, figure out where in the text file the issue was.
Yeah.
Try to fix it, rerun the program. No, in image-based programming languages, you update the program while it's running. So you literally are able to like redefine your controller function. Like if you found a bug, you can just say click a button and it will say redefine, and it reinserts it into the program while it's running. So you don't even have to restart it.
So I'm still the one changing it, but I can do it while it's running.
Yeah.
So instead of shutting down the machine, like getting in with my toolbox, fixing stuff, and then starting the machine all the way up again, I'm able to like use a little interface to tell the machine to fix itself internally while it runs, and then it can edit itself as it's going.
Yeah.
Okay.
And that's, I think like the more you learn about how computers work, the more you realize that that's kind of a radical idea.
Yeah, that feels very weird. I don't know if I can think of many real world machines that kind of work like that,
Yeah, but also in a way, like societies do work like that.
Yeah.
Like if something is broken at a factory, do you shut down the whole I mean, maybe you do, but if it's something small, do you shut down the whole factory just to fix that small thing? Like, exactly. No, you fix it while it's running.
Yeah.
And I mean, computers, they're like simple creatures, they're running instructions in order. And so how does a computer even do that? That's kind of like a radical idea. And so it's a really deep idea. And there's a funny thing that I'll just say at the end here that I forget exactly how the phrase goes, but it's like any sufficiently complex program will reinvent some flavor of Lisp. And what they meant by that is, if you have a sufficiently complex program, you don't want to have to restart it every time you want to fix something. So they're going to try to figure out a way to basically fix it in place. And that's what they meant. But Lisp said, why don't we take it to the extreme? Why don't we just make the entire program by default like redefinable at runtime?
So what sort of programs is it just anything that is sophisticated enough ends up essentially being Lisp or something like Lisp, or are there like particular sets of programs that end up using Lisp, right?
So I think That is a subtle point because there are like two flavors of programs, right? There's programs that you have a small task you need to be done.
Sure.
It does it, and then you're done with it.
Yeah.
You know, like if I'm converting my Word document to a PDF, that's not something I do very frequently. It's not something that needs to always be running.
Sure.
On the other hand, if I have an operating system, for example,
Yeah.
I mean, anytime my computer is on, the operating system is running. Or let's say I have a web server. The web server is always running. People are always visiting my website.
Yeah.
So these sort of long-lived problems, I think, naturally fit this idea where you're like, you know, like this is running for a long time. I want the program to potentially evolve. I want to handle issues as they come and not have to bring down everything.
Is artificial intelligence like large language models? Are these programs, are they using Lisp, or are they a different category?
So there are programs in a sense.
In a sense, but not in the sense of a traditional program that's like, you know, running a website.
Yeah, so like I guess I just mean that there are many layers to what we say when we say AI, right? Like there's the model,
Yeah.
which is like the result of training it. And that's just like, let's say a math equation,
Yeah.
you know, like a secret math equation. But when you open chatgpt.com, you're going to a website, right? There's a web server there.
Okay.
Then when you type into it, what's happening? You're sending your chat message to the web server. The web server is, you know, maybe it spins up the model. Maybe it sends it to the model and it, you know, comes back to the web server. But then maybe if there are millions of people chatting to ChatGPT at the same time, they don't want to, you know, start up and shut down the server for each person. Start up and shut down the model for each person. So then maybe they're like trying to get it to do multiple requests at a time. But yeah, fundamentally, Lisp is just like, so at a literal level, Lisp is like a syntax, like it's a way of writing that human readable text.
Mm-hmm.
But on a deeper level, it has this idea of like redefinability. So not everything is a Lisp. Like actually, Lisps have almost completely fallen out of favor in the modern world, as well as Smalltalks.
Yeah.
Languages have kind of converged actually on something pretty close to C and C++ and Python.
What's the name? Is there a name for that family of coding languages?
We generally call them procedural.
Okay.
Procedural in the sense that they run from top to bottom. Like if you write your code, it just goes boom, 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 boom.
But other languages don't do that?
Languages do that like all languages of course do that to some extent.
Yeah.
But there are like functional languages but they're like, okay, what if everything is a function? And like these tend to be super mathematical languages. Yeah. Like at least they feel like writing math theorems. And then there's, you know, object-oriented programs, which used to be in favor, have since fallen out of favor, I would say.
Yeah.
Then there's Lisp-like languages. But I think the procedural one.
So essentially, any website I visit will be a procedural coding language.
Probably. Yeah, I mean, Java's still there, but that's sort of the direction that the world is moving in.
Okay. Do you have anything else to add about coding languages before we go into our next topic?
No, I don't think so.
Well, for our next thing, you said timekeeping, analog, and digital, and I'm very curious about this one, Runi. So tell us what you think about timekeeping. If you have anything to show off, feel free to, and we can describe it to those who are just listening.
Well, So I'd say like maybe about a year ago, I got really interested in time, like in a practical sense, like how do we keep track of time?
Yes, this fourth dimension that we
Yeah.
move in. Yeah.
And this is like way too broad a topic for me to pretend to be an expert on, but
Yeah.
like the first thing I was curious about was, the most fundamental thing to me, like how does a clock work?
Yeah.
It's like, okay, like first of all, what type of clock are we talking about? So I was like, I don't know, like let's talk about a watch.
Yeah.
But then there are two types of watches actually. So there are mechanical watches and there are digital watches. There's also like quartz watches, which maybe we'll call digital.
Okay.
So analog watches have been around since like 1700s. Like we didn't have computers then. Like how are we keeping time?
Yeah.
And it's a really magical thing. These little machines are literally just gears, like metal gears inside a little thing, and they're powered by a spring that's wound up pretty tight, and that spring is slowly unwinding throughout the day.
Mm-hmm.
And that's delivering energy, and that energy is pushing these gears around in a circle. And
but my mechanical watch takes batteries. Is that just powering the spring?
So then it's not a mechanical watch, probably.
Even though it's analog?
Yeah, so...
Oh, really?
So there is a distinction here. Analog, I should maybe clarify, usually refers to, like, the physical hands on, like a traditional clock.
Uh-huh.
That's analog. Mechanical refers to how those hands are actually being moved.
Oh, okay.
So when we say mechanical, we mean they're being moved by these gears, this gear train.
Mm-hmm.
If you guys haven't seen a video of how a watch works, I would recommend looking at it. It's pretty cool, and it's pretty cool that they've been doing it for so long. Really intricate work, which is why these are luxury items in the modern day. So we have better ways of creating watches, objectively, in terms of precision, in terms of lifetime. But this, like, sort of like, it's almost jewelry at this point, right? This artisanal act of creating these gears, designing it, decorating it. So, for a sense of scale, like, watches in this category start around $500.
Okay, wow.
Decent watches probably get like $2,000 to $5,000.
Mm-hmm.
You're talking about a Rolex, you're talking about $10,000 plus. And these easily go up to hundreds.
So these fancy watches, they are largely name brand, and that's why they're so expensive, but it is also because the quality is just actually higher.
Yeah, it is a mix. I'm not going to sit here and pretend like a $10,000 watch is worth it for everybody. It's really is like an emotional thing, and that it is a little bit of a slippery slope at that point. Like, but in the modern day, watches are inherently luxury items. Like, there's so many things around us that we can tell time on.
Mm-hmm.
But anyway, so that's more like the jewelry side of things. The watch you're wearing, I suspect, if it takes batteries, it's probably a quartz watch.
Yeah, it's like a $50, like, pretty plain analog watch.
Yeah.
Yeah.
And those are going to be, I kid you not, like, orders of magnitude more accurate than the most expensive mechanical watch.
Because,
like, I don't care how much money. It's the technology. The technology is just that much better. And
well, if it's not gears turning it, what's turning my analog watch right now?
So probably gears are turning it, but it's not driven by A spring.
A spring, okay.
So it's driven by a battery.
Yeah.
And the reason why that is so accurate, more accurate than a $500,000 watch, is because of the quartz crystal inside it. So someone realized, if you ever seen like a tuning fork, right, it vibrates at a certain frequency.
Yeah.
Quartz vibrates at a certain frequency, like 30-something thousand, I don't know, hertz. Yeah. And you can power it with your battery, and that's going to be way more accurate. So we know how many times it vibrates per second. So then it's just a matter of like dividing it up evenly enough to get it to like 1 second. You know what I mean?
And if you do the calculation precisely enough, you're getting like an exact second, essentially.
Yeah. Okay. And so these calculations are, as a tangent, are like basically how many notches to put in the gear, like how many notches to put in the circle. So like if I put 60 notches in a circle, how that means it'll take 60, spins around to go like one full circle.
Yeah.
So then when you layer on different gears, like you have a gear turning another gear, that's where it like sort of ends up dividing, and that's how they like get to 1 second.
And do you know if the quartz is a significant factor for it costing more, or like the actual mineral?
Quartz is pretty cheap. It's cheap. Okay. It's they can grow it in labs. They can manufacture it at scale. They don't need, really humans involved.
Yeah. Okay.
But you do need to change out your battery every now and then, because it takes more energy. There are some. Sorry, go ahead.
No, you go first.
I was going to say that there are some like interesting, quote unquote, cutting edge watchmakers out there who are trying to mix the two. They're like, oh, what if we power the watch by a spring, but it's powering a quartz crystal?
Oh, okay. So that makes it precise, but also fancier. Okay.
Exactly. So that's called, the company is called Grand Seiko. Mm-hmm. The technology is called Spring Drive.
Yeah.
And you can get your hands on one for the low price of $5,000.
Okay. What is the lifetime? I mean, does the lifetime range pretty significantly with mechanical watches? Like based on the quality? Like what's the lifetime of these things?
That's a really good question. So your quartz watch, its quote unquote lifespan is the lifespan of its battery.
Yeah.
And to cut corners, to cut costs, I should say, manufacturers of quartz watches will sometimes make it so that you can't replace the battery. Really? Because it's more expensive to, have screws there so that you could take it out and replace the battery.
Yeah. They'd
rather just like glue it on. So then you're kind of out of luck after, I'd say 5 to 10 years are usually. So, I mean, it's a pretty decent amount of time. But yeah, I mean, and of course, more expensive quartz watches, you can change out the battery. So then we're talking about, if you change the battery like every 5 to 10 years, some quartz watches will even be solar powered. Okay. So you can extend it a little bit more, like maybe every 15 years. Even solar powered quartz watches are like $150, like much cheaper than mechanical watches. Sure. But definitely still luxury items. So mechanical watches, part of the reason that people adore them is because they are like heirlooms. So in theory, because of the build quality, because they're not driven by batteries, they don't really have a lifespan.
Really? Okay.
At least that's what the watchmakers would like to tell you.
Okay.
So they're like, oh, okay, yeah, this is something that, I mean, it costs $5,000, but, imagine handing it down to your son one day. That's sort of how they get you.
And they advertise it as like timeless, and a bit of irony for the watch,
yeah. In reality, you are going to need to service a mechanical watch every 5 years.
Okay. So same
so
relative lifespan in a sense.
yeah, you're really not like saving much money. You're really not saving money by going mechanical.
Yeah.
But what they're going to do is they're going to still keep the spirit of the watch, I guess. They're just going to disassemble it, lubricate it, make sure everything's running. They'll take it apart basically and put it back together.
That feels a lot more intrusive than just putting in a new battery,
Yeah, it is. But I guess it goes back to like the artisanal aspect of it. Yeah.
Do you have any watches that you want to show off to the audience?
Yeah, I might be. I have this watch. I've been. Can't really see it that well.
You can see
it. I got this about a year ago.
So it's like a white face. For those listening, white face, a darker wrist strap. It looks rather nice. Yeah.
Yeah. So I don't know if you can see it here, but there's like a triangle at the top.
Okay.
That's indicative of a pilot's watch. It's a type of watch, obviously not exclusively worn by pilots, but historically worn by pilots. That triangle at the top helped them sort of orient where 12 was, no matter, what angle they were sort of looking at it while they were flying.
Oh, okay. Very interesting.
So you'll see with these types of watches, they'll typically have like Arabic numerals, like very visible numerals.
Yeah.
They're usually larger. So that's all this this history of like being a tool.
Yeah. Because if it were Roman numerals or less legible, the pilot in a crisis would have to could potentially mess it up easier. Okay.
This particular watch is a Mark 20 from IWC. IWC manufactured actually some very historically significant pilots' watches. So
yeah.
The first Mark watches were worn by, British fighters around World War II.
That's really cool.
So they were like the designated manufacturer of them. They were also a different line named the Big Pilot was the designated watch of the German Air Force during World War II, but we don't talk about that as much.
Sure.
But one thing you'll notice about in this hobby, I guess, is that maybe this is just like guys being, masculinity in modern society, but we're sort of obsessed with these watches being tool watches and having this heritage. It's like,
yeah, like I want to explain the history of World War II pilots when I talk about my watch. Yeah.
Yeah. Or also like I want to wear my watch because, like I'm just such a adventurous guy and I need a watch that can keep up with me.
Yeah.
So I don't know, like on the one hand, I appreciate the history. On the other hand, I do sometimes get a weird feeling because I'm obviously not a pilot.
Sure.
Like it's a luxury object. Like, who's spending thousands of dollars for something that they actually intend to, get dirty or get scuffed and do work in? I don't know.
Because I've seen watches, and I've seen like nicer watches where they still, like, it's not just the simple interface like yours. There's still all these like little miniature clocks and these numbers and stuff that it looks very much like something that someone like trekking through the forest or something might need. But then, when you have one of the luxury ones of those, that's basically a richer guy saying like, yeah, I'm pretty wealthy and I use my wealth for this thing that I'm supposedly using for practical reasons of like, I'm like a big adventurous outdoors guy. Whereas a guy who has like a more simple interface might be portraying himself as more of like an indoors business type, stuff like that.
Yeah.
Okay.
Yeah, so you either have rich people cosplaying or rich people being so rich they can afford to get their $10,000 watches scratched and...
Yeah.
Yeah.
That's pretty funny. I want to move on to our final topic of our episode today, which is about cooking as an adult and especially integrating one's own culture into that. And I definitely want to ask about the yeast as well. as a part of this discussion. But yeah, tell me about cooking as an adult.
It was not something that I did until I was an adult, really. I mean, I made scrambled eggs, and then when I met my girlfriend Diana's mom for the first time, she asked me, "So what do you cook?" Like presumably, I guess to see if I could take care of her daughter.
Yeah.
And I was like, scrambled eggs. I don't think it was the strongest first impression, but
Sure.
yeah, I feel like if it was just me, honestly, I might not have gotten too much into cooking. Like, man, I love scrambled eggs. I could eat that all day.
Oh, sure, yeah.
But as soon as you're cooking for someone else, it's not just like a matter of like what they want, but it's also, for me, it's also like an expression of like care and love that I'm like putting time into something and I want to make someone happy when they eat my food.
Yeah.
So that's sort of how it started out for me. I was a total beginner, and I think so I mean, like, I got the cookbooks, I got the pans and stuff.
Mhm.
Really, it's just a matter of, I think, learning about ingredients.
Okay.
I think when you're developing as a cook, when you can sort of look in your fridge and be able to whip something up, I feel like that's a pretty good, that's a pretty advanced skill, and
Yeah.
I can't say that I can do that all the time, but there's like a certain understanding of ingredients that goes into it.
And there's also the whole balancing of different types of like flavors, so like the sour and the spicy and the bitter and everything, and like knowing which spices do what, and like trying to have a balance, but one that's not so balanced you can't distinguish.
So a super famous book, a cookbook that had a big impact on me as well, is called Salt, Fat, Acid, Heat.
Okay.
And the entire book is just essentially structured around that idea you said, Peter. But they break it down into these 4 components of cooking: salt, acid, fat, and heat. And by the way that you distribute those 4 things and the way you play with those, that's like where all the magic of cooking is.
Okay.
Yeah.
And so like different fats produce different results. The acid is just like different acidity of different foods will impact like just the taste or like the process of cooking, or
both. I mean, like if you have a dish like ceviche, which is basically raw fish in a very acidic liquid, that's in a sense the acid is cooking it. So there is like chemical reasons, there's taste reasons for sure. Salt always brings out water.
Yeah.
So you'll often see, like in pasta recipes, they'll say put the onions and then put salt. Yeah. And the reason they do that is because they don't want the onions to get soggy. They want to get the water out. They want to get it evaporated.
Oh, okay. And salt will also enhance flavor, if I'm correct.
Yes. Yeah, very interesting chemistry there.
Yeah. And then with the heat, what oils do you use? Do you always use one type of oil when you're cooking? Do you use different ones depending on the food?
So oil is more fat, but I do use different. So like, you always want to have a neutral oil. So neutral oils don't really impart flavor. We're talking about like avocado oil, vegetable oil.
Yeah.
There's, on the other end, there's like, I should say like also those neutral oils, you can cook on much higher heat with them usually. So your pan can get much hotter. But then you have stuff like olive oil, which is not a neutral oil. Olive oil has a distinct flavor.
Yeah.
It also has a low smoke point, which means that you can't cook on it with high heat without it getting this burnt taste.
Yeah.
Other fats are like, butter, ghee, which I guess is sort of like a nice transition into the cultural component. I don't know if you know what ghee is, Peter.
No, I don't. I want to ask about ghee. Before I do that, I actually went to an olive mill today. Yeah, so Arizona has a single olive mill. It's in Queen Creek, Arizona. It was like 40 minutes from my house. I went there. They were very much saying you should use olive oil for every single thing you ever do, essentially, which makes sense. But they were saying like take a spoonful in the morning. Make sure you can use it in cooking. Like it's great for cooking. Don't worry about the flashpoint. They had some very interesting olive oils as well. They had some blended ones, some infused ones. So they had like stuff you might expect, like rosemary and basil olive oil. They had this dark chocolate olive oil, Runi, that literally it tasted like chocolate syrup. Like I could have put that on ice cream and it would have been great. They mixed that together with I think like a strawberry, balsamic or something. It was crazy. It tasted really good. So I definitely like quality olive oil. But you're saying it should be used more as like a finisher on something,
or low heat.
Low heat. Okay.
But yeah, like you're saying, I think, admittedly, only recently have I been able to distinguish quality olive oil from
Sure.
The cheap one. But it just has such a distinct and rich flavor that sometimes I just make a salad. I just put olive oil in it. You don't even really need a dressing.
No,
it's
don't.
High quality olive oil.
So then tell us more about ghee. Explain a bit more about your own cultural heritage, how that plays into cooking.
Yeah, so my parents are immigrants from India.
Mm-hmm.
So I grew up eating Indian food, South Indian food in particular,
Okay.
because actually Indian food is not I don't know the word. It's not one thing.
Sure.
And actually the food you eat at restaurants is, first of all, it's more leans towards more North Indian in America.
Yeah.
And also restaurant food in both the North and the South is very different than the food that we eat at home. We're not eating like butter chicken and chicken tikka masala at home.
Yeah.
That's those are very delicious and rich foods, but that's the reason we can't eat it all the time, because they're very heavy in butter and they're very fatty.
Well, so first off, what are in a very general, simplified sense, what's the difference between more North Indian and South Indian? And then, tell us more about the food you eat at home.
So, to be honest, I can't say a lot about it because I just don't want to misspeak. Okay. But North Indian food is typically milder in terms of spice. Typically, you'll use more rotis and bread.
Yeah.
South Indian food is spicier and rice heavy. So, but also just the actual dishes that we cook are different. The spices we use are slightly different. Mm-hmm. So, I think after a while of cooking, and I was starting to get proud of telling my family I made this today.
Yeah.
There would always be some questions that oh, do you cook any Indian food? Mm-hmm. I was not really. And it kind of bothered me after a while.
Yeah.
Because it was I'm learning all this stuff, and I'm not really learning the food where I came from.
Yeah.
And so there were I slowly started to do that. Obviously through watching my mom when I got home, but also there were little traditions, So Indian households, they'll have a few things that are sort of handed down in a sense. So one, or that you make. So one is yogurt.
Yeah.
Indian households often make their own yogurt. Mm-hmm. And actually they share. So the way you make yogurt is it's a bacteria, right?
Yeah.
So you start with the culture. It's kind of other types of bread and stuff, but you start with the culture. You put it in pasteurized milk, and you let it sit at around 100 degrees for 10 hours, and it'll turn into yogurt.
Yeah.
And so, but you need that culture to start. So Indian households will often share that culture and pass it down.
Yeah.
And so one of the things I did was take a sample of my mom's culture when I visited home. I took it back to Boston, where I live, and I've been, making it ever since.
Wow.
The other things that you learn are like, like you make ghee. So ghee it's often called clarified butter. There's actually a slight difference. But basically it's butter with sort of the, like a bit of the water evaporated.
Okay.
And so literally what you do is you put butter on a pan.
Yeah.
And you just like let the water evaporate for a bit. And after a while, like some of the particles in the butter will fall to the bottom of the pan.
Mm-hmm.
They'll get a little bit burnt. And then at the end, you pour it out and you let it cool, and it turns into this solid thing, kind of like butter.
Yeah.
But it has two notable things, and the most notable is that it tastes like quite a bit different, actually.
Yeah.
It tastes a lot nuttier. And it also has a much higher smoke point.
Oh,
So
okay.
it's very suitable for cooking.
Yeah.
And yeah, so we use ghee a lot. Like instead of butter, we'll often use ghee to make something richer.
Is it something you always make yourself? Is it something you buy at the store?
I tend to make it myself.
Okay. Nice.
It's just another one of those traditions,
Yeah.
that sort of connects me with my culture. Another thing is like ginger garlic paste.
Okay. That
It's
sounds
literally just, yeah, like ginger, equal parts garlic, maybe some oil,
Yeah.
maybe some turmeric. And you just blend it all together and you just keep it in a jar in your fridge.
Yeah.
And it's a little hack, honestly, because even when I'm not cooking Indian food, if something says use fresh garlic, I'll just like put a spoonful of that ginger garlic paste in.
Okay. Yeah, that sounds delicious.
Yeah, I mean, they're like, each family has their own garam masala blend, which is, garam masala is like a all-purpose seasoning.
Mm-hmm.
It's just a mix of various spices. But the actual, proportions are sort of like each family has their own.
Okay.
Yeah.
Is it a family secret, or is it just something that is custom for each family?
I guess it's not really a secret.
Sure.
But also, like, I don't know if it's really something that people measure out. It's probably just like an intuition developed.
Okay.
Yeah.
And I remember you telling me at one point that this culture is not just from your mom, but ultimately came from India. Is that correct?
Yeah, that's right.
Okay. That's really cool. So, at what point did it cross over to America? Was it your mom's generation, your grandma's?
Yeah, my mom and my dad were both the first in their family to come.
That's really cool.
Yeah.
Is it just your mom's side that you're getting the culture from? Does your dad have his own culture?
So they're both from the same part of India.
Okay.
So I was definitely, equally influenced by.
I mean the actual culture thing, like the physical culture.
Oh, you're talking about the yogurt culture.
Yeah, the yogurt culture.
That's from my mom's side.
Okay. Does your dad could he have brought over culture if he wanted to?
Yeah, I'm sure. Like I think my grandmother probably still makes yogurt.
Okay.
Yeah.
Okay. Very cool.
Yeah.
I'm sure Diana is very happy that you're becoming a much better cook, right?
I think so. I sometimes experiment a bit too much.
Yeah.
But it's all for the better good.
Yeah, I'm sure she gives you some constructive criticism.
I think the hardest thing, honestly, was that she ate a lot more meat than I did growing up, and seafood. I barely ate any seafood growing up.
Okay.
And when I ate meat, it was pretty infrequently. I think, like most Indian households, we only ate it once a week, twice a week, but not very frequently. So transitioning to eating meat more was a challenge. I don't. Maybe challenge is not the right word, but it's just like, something to adapt to, I guess.
And what's been your favorite dish that you've learned how to make in this cooking renaissance of yours, Runi?
Oh, that's the hard question. Gosh, I always blank on this question.
You can give an example of one of your favorites, maybe from more recently.
Well, so this is the first thing that came to mind, but I started making this Szechuan sauce.
Okay.
So I've been putting it in I've been sneaking it into everything.
And what goes into a Szechuan sauce to begin with?
So it's basically just hot red chilies, onions, a few spices, and sugar.
Okay.
And so this is actually from Indo-Chinese cuisine, which I took an interest in somewhat recently because I just think it's fascinating because you'll hear of dishes like gobi Manchurian or Szechuan fried rice in India in the same breath that you'll hear traditional dishes.
Interesting. Okay.
So I was just so fascinated that this Indo-Chinese cuisine had become so integrated into Indian culture.
Yeah.
There's a really interesting history there of and it is very distinct from the Chinese culture, like the Sichuan cuisine of the Sichuan region in China. Yeah. It is a very different cuisine, actually. Okay. So they share a name, but they are. It's sort of like that adapted to Indian tastes, which literally was the migration story.
Yeah.
But so that's where it's from.
Your Szechuan sauce is the India-fied version of the Chinese version.
Exactly.
Okay.
Yeah.
Cool.
Yeah, I've been putting it in everything, man, and it just adds a nice kick to everything. And yeah. Oh, how did I forget the main ingredient of the Szechuan sauce is the Sichuan peppers.
Yeah. Okay.
Those are not like the red peppers. Those are actually little flower buds. They kind of look like black pepper.
Yeah.
If you've eaten Sichuan cuisine, you might have gotten this numbness in your tongue.
Yeah.
That's the Sichuan pepper.
Those little peppers you really don't want to bite into, or else your mouth goes on fire. Okay, yeah. And so those are used in the sauce. That's really cool.
Yeah.
Well, as we wrap things up, Runi, I have a question I ask all my guests at the end, which is just, what is one piece of life advice you'd like to give to anybody listening to the podcast?
I would say, don't be ashamed to have a lot of interests and to be exploring a lot of things, because that's honestly something that until recently I felt a lot of shame about, because at first it was all my math professors are like, you need to spend more time on math if you want to take it seriously, if you want to go into a PhD program. But I loved math, but I also loved programming, and I loved art and writing.
Yeah.
And I feel like a lot of times in life people are like, you need to buckle up and just do your one thing and become excellent at it. But I never felt that was the path for me, and I think that my life is richer because I continue to explore many things. So I would just encourage people to do that as well, if that's what they're interested in.
And that's what this show is all about, is exploring different interests by listening to different experts and people passionate about it, talking about it, being a jack of a couple trades and then relying on everyone else around you to know all the other ones. And so that's really a very poignant and wonderful point, Runi. So, and that concludes our show. Thank you so much for coming on today, Runi. It's been such a blast. I've learned a lot about stuff that I normally don't touch, like math and programming languages and all that stuff, and you were very knowledgeable. You got basically all my follow-up questions, and it's clear that you are very passionate about these things. So thank you so much for being willing to spend the time to come on here.
Thanks, Peter. I enjoyed it. I've descended into darkness, I see, as this podcast has gone on.
No, it's been such a great time. You can find more of our episodes on Spotify and YouTube at A Deck of All Jacks. I am your host, Peter, and I will see you next time. Bye.